All right, so another math video. So we are going to be talking about special segments inside circles. So as you can see here, we've got some special segments, A, B, C, and D. And these segments, A and B, and C and D form chords, right? A chord is anything that goes from one side of the circle to the other. So a diameter would be an example of a chord, and a diameter is just a special chord that not only is it, a chord, but it goes through the center of the circle. So in this diagram right here, I'm going to tell you that that point is not the center, or at least not necessarily. And this is kind of cool because the way that these chords intersect can be defined by AB equals CD. So the lengths of A and B, when multiplied together, should equal C and D multiplied together. That doesn't mean that A and C are equal, or that A and D are equal, or B and C or B and D. That's not the case. But when they are multiplied together, whatever their lengths are, it will come out the same as these two being multiplied together. And we can use this interesting property to solve a lot of complex problems, right? So where does this property come from, and why do we know it to be true? That's what we're going to prove. So we're going to prove that this property is true, that the two parts of the chord multiplied together are equal to the other two parts of an intersecting chord multiplied together. All right, so first thing you're going to do is you are going to want to draw some lines in and make some triangles. So now I've made two triangles. I've got a triangle with length A and C together, and I've got a triangle with D and B together. All right, so now that we have that, we're going to try and prove these two triangles similar. And then thus their parts proportional. So our first job is to prove that these angles are congruent. So let me grab a pen. This angle right here, which I guess I have not named, maybe I should put some dots or some names for my dots on these circles. Let's go X, Y, and Z, and maybe W here. And then in the middle, I guess we'll do E. I've got a student who prefers E for the center for unknown reasons. All right, so, for the point of intersection. This is not the center of the circle. All right, so we know this angle right here, XWE, is congruent to this angle here, XZY, because if you notice, this is an inscribed angle, and this inscribed angle opens up to this arc. Well, so does this inscribed angle. Therefore, they must be the same. So I'm going to write that down. I'm going to write that angle XWE is going to be congruent to angle XZY. And we know this to be true because they are inscribed angles opening up to the same arc. So we just say by inscribed angles. All right. So one set of angles down, we can prove that this angle right here and this angle right here are similar or are congruent in the same way. They are both inscribed angles and they're opening up to arc WZ. So I'm going to say that angle WXE is congruent to angle ZYE. And we know this to be true because, again, inscribed angles. So they're congruent by the same dumb thing, right? All right, so our last angles. Probably the easiest ones if you're aware of what's going on, perhaps the most difficult if you're not. This angle right here on this triangle is going to be congruent to this one by vertical angles. You could also say by, algebra. They have to add up to 180, and if we know these two, then we know the remainder, right? And if we know these two, well, that's going to be the same remainder. But we're going to go with that these angles, XEW, is congruent to angle YEZ, because of vertical angles, right? These two have to be the same. That's our scissor theorem. So vertical angles. All right, so now that we have all three angles set up, we can say that the triangles are similar by AAA. So I'm going to say that now. We know that triangle XEW is similar to triangle YEW by angle, angle, angle. And we know that because of the above, right? Those are our three angles in the angle, angle, angle. All right, so now that we've shown the triangles to be similar, we can prove their parts congruent. So I'm going to fold this over so I've got a little bit more room. You can still see the diagram. This is the second part of our proof. So now that we know the triangles are similar, their parts must be congruent. So therefore, now that I've shown the triangles are similar, their parts are going to be proportional. So this part right here is part C, right? And it's going to be proportional to part B. And A is going to be proportional to part D on the other triangle. So let's write that. So A is proportional to D in the same way, so that's our equal sign, as C is proportional to B. Now, this kind of looks weird because you'd think, oh, both the blues should go on top. But really what's happening is this part on this triangle, triangle 1, is proportional to the corresponding part on triangle 2. Well, in a similar way that this part on triangle 1 is proportional to this part on triangle 2, right? So the things on the first triangle, A and C, go up top, and on the second triangle is B and D. And through this magic, we can do some algebraic manipulation. We can multiply by B to both sides, right? And we can multiply to D to both sides, and it moves the B and the D over. So what we end up with, I guess I won't show it, is that B ends up over here with the A, and over here, C ends up with D, which is exactly what we wanted to prove. So we've proven that because these triangles are similar, their parts are proportional. So I wrote that, showed what parts are proportional. A is proportional to D the same way C is proportional to B. And then through the magic of math, we were able to move things over and show that A times B should equal C times D. And that is our proof. Not too bad. So we've got two parts, right? Part 1 showed that the angles are congruent. Therefore, the triangles are similar. Therefore, their parts are proportional. The key thing to remember is that you need to draw these lines in to form these triangles, and then have at it with these inscribed angles. Again, always be looking for inscribed angles when you're doing these proofs. It's the key, vertical as well. All right, so that's proof number 1. That's AB equals CD, and that is true for parts of a chord. So we call this the chord product theorem. Product meaning multiplication, because that's what's happening, A times B and C times D. And chord-chord because it's two chords crossing. All right, so that's the chord-chord product theorem proof. Let's go on and check out the next one. All right, so these are chords, part A and part C, but they aren't intersecting. So this is not going to apply to the chord-to-chord product like we did last time, right? See how they intersect? These are actually a special kind of chord that extends outside the circle, and we call those secants. So this is the secant product theorem. And again, product is coming up because we are doing multiplication, right? A plus B, which represents the whole thing, is being multiplied by B, the outside piece. And that should be equal to C plus D, the whole thing, right? Times its outside piece. So the product part comes from this multiplication between this idea and B and this idea and D. So we're going to prove that, and we're going to do it in the same way we did the last one. We are going to make some triangles, and then we're going to prove those triangles similar using congruent angles. So what we're going to do first is we're going to draw in a line. Okay, so we're going to connect from there to there. And what we're going to use is remote interior angles theorem to prove that these angles are congruent between these this triangle that we've drawn. So first off, I am not doing this correctly. I need to draw one more line in. Sorry. All right, so let's draw another one in. 2 lines. There we go. All right, so now we've got 2 triangles. We have this triangle right here, Y, and then intersection at Z, and then we'll have this be, how about W and U? Not really in order, but we'll do it. All right, so the triangle XWZ, this triangle right here, we're going to prove that that triangle is similar to triangle UYZ. Okay, so the bottom triangle here and the top triangle here. So what we need to do is show that their angles are congruent. So what I'm going to do is I'm going to start out with this angle and this angle, and I'm going to point your attention to that these angles are inscribed angles and they open up to the same arc. So therefore they are congruent. So let's call it angle X, because that's the only angle X, and angle U. They are congruent by inscribed angles. There we go. All right, and we know that this angle right here is shared between both triangles, right? We have triangle XZW, this triangle right here, shares that angle with YUZ. So we have angle Z is congruent to angle Z by shared angles. right? This angle right here, UZY, is congruent to angle XZW because it's shared. I guess we could have written that instead of angle Z, but nevertheless, we'll move on. So now that I have these two angles, and I've got, I'm sorry, these two angles and these two angles, I can get the next one for free. I guess we're not doing remote interior angles after all. These are going to come for free through algebra, right? We know that the remaining angle here with this guy is going to be a certain amount, right? 180 minus whatever these are. And the same thing for this angle right here for this triangle. It's going to be 180 minus whatever these are. Well, because these are the same for both triangle, whatever's left over after subtracting them from 180 will be the same for both. So these two angles, let's call them angle, let's go angle UYZ and angle UYZ. We've got XWZ as well. They are going to be congruent, and we can say, just by algebra, I know that you mean by the interior angles of a triangle, right? They all sum to 180, therefore blah, blah, blah. You do the math. That's the algebra part. And so therefore, we know that these two triangles, triangle XZW, yes, XZW, is similar to triangle UYZ. Okay, so with that information, we're pretty similar to our last proof. Now we're going to show something cool about their sides. So let's do that. So I'm going to fold this up, just like I did last time. So we can see the diagram. All right. Cool. So now our next part. So now that we've proven the triangles similar, we can talk about their parts being proportional. So the long side is AB, right? A plus B. And that is going to be proportional to the long side on the other triangle, which is C plus D. In the same way that the other parts are proportional. So you got to be careful on this one. This triangle right here is A plus B, D, and then this length right here that we don't have a name for, right? Whatever XW is. So the other part on the first triangle is part D. So that's going to go right here. And the other part on the bottom triangle, again, here's CD, right? B, and then the part we don't have anything for. So the other part on this triangle is going to be B, and that's going to go below because it's with the second triangle, just like C plus D was here, right? So first triangle stuff on top, A plus B and D. Second triangle stuff on the bottom, C plus D and B. So now, after we've shown that these are proportional, we can do some magic and move the B over to be with the A plus B. So we have A plus B in parentheses times B. And we'll move the C plus D over to be with the D. So we've got C plus D times D. And we've proven what we set out to prove. So there it is. So again, to break it down, I proved that the triangles that I drew, and I drew those triangles by drawing two lines, right? I proved that they were similar by doing angle, 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 right? I should probably write that, by angle, angle, angle. And here are my three angles that I found. Two of them were inscribed, right, the two green ones. They match to the same arc. I found one set of shared angles for both. And then I also found the last set of angles because of the interior angles of a triangle have to add to 180, and if I subtract these two and they're both the same, then what's left over must be the same. So we get these two for free basically by algebra. And then I went to my next part of my proof, right, and found that the parts are proportional because the triangles are similar. The stuff from the first triangle, right, on top, and the stuff from the second triangle on the bottom. And then did some algebra to move things around to get to the form I wanted. So this is the secant-secant product theorem. If we know what A and B are, we can solve for one of C and D using this. So you'll have to do this as a proof and do some examples, just like the last one, where you'll be asked to solve for some variables. All right, so last little bit on segments. So we've seen what secants do, right? It's these guys. They go outside the circle, hitting the circle at 2 points before exiting. What if we were to slide this down, right, further and further and further until this line right here was hitting the circle at exactly just 1 point? Well, we'd call those tangent lines, and they'd look something like this. So imagine, if you will, this line was going through the circle, right, hitting it at 2 points. That was a secant, and we started sliding it down further and further and further until it finally just hit it at 1 point exactly. Well, you'll notice that as we do this, part C gets smaller and smaller and smaller until it becomes 0. And D gets bigger until it's all the way as big as it can be without going off the circle. So C disappears and D becomes bigger. And same thing if we do it to this one. A disappears, right? And B becomes bigger. So A is gone, C are gone, and what we're left with is B times B equals D times D, otherwise known as B squared equals D squared. So if B squared equals D squared, right, this thing's B squared and this thing's D squared, or vice versa, then these two must be equal. So what we're trying to prove here is that AB is congruent to CB if these two are tangents. Okay, so what we're going to do is we're going to construct some stuff, just like we were in the last ones. We have a circle, so there should be a center somewhere. Let's mark it. All right, from that center, we're going to trace out a line to the edge of the circle where the tangent meets, the point of tangency. And we're going to do that here as well, which we can always do, right? You can always draw a radius from the center out to the edge of the circle. And because these are radii, we know that these two are congruent. So I'm going to write that. So let's call this point X. So we know that XA is congruent to XC because radii. Cool. And then if we are also to construct a line between X and B, like this, we've created for ourselves two triangles. Now, a thing that you need to know about tangents is that when we have tangents, they hit the point of tangency and intersect with the radii that hits that point of tangency at a 90-degree angle. So these are 90 degrees. That is very important. So using this information and noticing that we have a shared side, let's go with purple. A shared side, right? They both share this side, these two triangles right here. We can prove that these triangles are congruent. So we know that this and this are congruent because they're radii, and we know that XB is congruent to itself by shared side. We also said that these angles right here are 90, so let's write that. So angle XAB is the measure of angle XAB is congruent or as equals the measure of angle BCX. Did I there? No, XCB, which equals 90 degrees. By definition of tangents. So because those are tangents, we know that they hit the radii at 90 degrees. So now what do we have here? Well, we have a hypotenuse leg. We have the shared hypotenuse right across from the 90. And we have two legs that match up. So therefore, these triangles are congruent. So therefore, triangle AXB, or XAB I should say, triangle XAB is congruent to triangle XCB by hypotenuse leg HL. Okay, cool. So that's our first setup. So we've proven the triangle's not similar, but actually congruent. So what does this mean? Let's fold it the other way. That'll be good enough, right? So now that we've proven these two triangles congruent, what do we know about these sides right here that we wanted to prove congruent? Well, we know that they are congruent because if the triangles are congruent, their parts are congruent. So we know AB is congruent to CB by our favorite reason, by CCP. Corresponding congruent parts of triangles are congruent. So if these triangles are congruent, then the corresponding parts are congruent. These correspond, so they're congruent. These correspond, so they're congruent. And therefore, these correspond because they are congruent. So we know that to be true by CCP, and that is our proof. So these are always the same. We also did a proof earlier when I talked about sliding this down and making C less and less, and A less and less going this, pushing this up, right? A and C disappear, we get B squared equals D squared, and if B squared equals D squared, well, this is B, and that's D. So B and D are going to be equal. But the main proof is this. Alrighty. So those are three proofs on special triangle segments. We've talked about tangents, proving that the tangents are always congruent from a point of tangency to the point of intersection. We've proven that secants are always congruent when you multiply their parts together, the whole thing times the outside piece. That'll be the same as the whole thing times the outside piece here. We've done that by drawing two triangles and proving the triangle's similar, and then showing that their parts are proportional. Then we did something similar here with chords, the chord-chord product theorem, showing that the pieces of the chords multiply together to equal the other pieces of the other chord. We did that by drawing two triangles in and proving the triangle's similar, right? We had some inscribed angles here, right? Top and bottom, and we had two vertical angles. So therefore the triangles were similar and their parts are proportional. A over D equals C over B. And then move things around to get this. So there's three theorems right there. And how to prove them. Utilizing these theorems is pretty easy. You set up and use these formulas, right? Whatever we've got here, if we've got x there, plug in x for b. If we've got x plus 1 here for a, wrap x plus 1 in parentheses and plug it in for a. I'm going to leave those to your imagination. Check out the homework. I'll provide the proofs. See you next time.